Okay, I'm going to start. So we're down to the final week. Congratulations, you all made it. This is sort of this has historically been a challenging time in the course because we've covered a bunch of topics that have sort of narratively made sense. They sort of built on each other. And now, in the final week, okay, so I kind of also understand you guys have a test you're worrying about now, and it's not this stuff. And so I don't want to bog you down too much with totally new material. The problem is, the last topic of the thing we want to cover is, in some sense, a kind of different approach, a kind of different way to think about things. So I'm hoping that in this final week, I can really just help give you guys some tools, some new vocab, and some ways of thinking about this different approach to kind of using computational neuroscience that falls into statistics and probability. Yeah, I guess I'm looking to help you out in this final stage. We're hoping that we can use some of the concepts here in your sort of final project for after the break. But yeah, so that's kind of the goal. So we're moving away from the dynamic stuff, and I'm going to sort of talk about something new. So I don't want people to get discouraged, to feel overwhelmed now that it's just the final week. What are you doing? Throwing totally new concepts at us, totally new ways of thinking. I really just want this to be useful for you guys going forward, right? Because this is sort of a big missing piece that you will encounter if you do sort of either work in data science, if you do work in computational neuroscience, or sort of any type of applied math today. Does that make sense? So please slow me down, or if you're unclear of my terminology, I sometimes fall into the bad habit of dropping words I maybe haven't defined yet. So please stop me if I'm using words that don't make any sense. The goal of today is to try to just take us out of really systems that up until this point, with the exception of the linear regression lecture, have been deterministic systems, have been basically modeling how things behave or modeling how things are, and not dealing with uncertainty at all. So the other major class of kinds of mathematics that we use in computational neuroscience, in sort of data analysis of all forms, falls in the domain of probability and statistics. And yeah, I'm just sort of admitting up front that this is kind of a different way to think about things. But I want to introduce you guys to these concepts, and we're hoping our goal will be to use sort of the concepts and the terminology we'll define over this week in sort of an application for your final project using that dynamical systems model that we did last week, the usual inhibition model. Okay? I mean, any broad questions or concerns about anything before I start? No? Okay, great. So, what I'm going to give you guys is the basic terminology for sort of the foundation for how we talk about probability, how we talk about statistics, and how we talk about statistical models. Some of these terms you'll have seen before. Again, the linear regression lecture was an example of a statistics-based lecture where I've used a lot of these terms. These terms are going to come back today. They sort of lie in a different space than when we were just thinking about dynamics and how things evolve in time. So I'm going to give you guys basics of notation for that so people understand this from the ground up. How we define models and parameters. Again, we did that in the linear regression lecture. Then we'll talk a little bit of the difference between what kind of probability is and what statistics is, and that can be thought of as sampling and inference, and I'll define these terms as well. We'll talk about distributions and different distributions, and we'll sort of talk about in the context of Bayes' rule. And then if there's time, and depending on how much I get through, we'll also talk about estimation, maybe today. It's important, and I probably should have done this way earlier in the course, but I'm curious I don't have a sense of everyone's background, especially as it relates to this exact thing. So how many of you have heard, let's say, with the exception of last Thursday, prior to last Thursday, how many people have heard of Bayes' rule before? Show of hands. Okay, so most of you heard of that before last week. Okay, good to know. And how many of you guys have taken a class in probability or statistics? Has anyone taken a class in probability or statistics? Okay, fair number. Cool. Good. Then we should be able to hopefully get through these big ideas pretty quickly. So just to reiterate, up until this point, we've talked about deterministic processes, just to try to keep everybody's concepts sort of compartmentalized in useful ways. We went through the basics of linear regression, the basics of linear algebra, and we talked about that sort of process. We use linear algebra tools to describe how things change in time. These were all deterministic processes. And what we're going to talk about today is how you interact with data in sort of a realistic way. Again, the other lectures where we've sort of done that would be the PCA lecture and the linear regression lecture. And the PCA lecture was, in some sense, deterministic. We didn't really have to think about probabilities in that case. And for the linear regression lecture we did, and we're going to revisit a lot of those concepts today. And of course, those kinds of concepts are used when we don't fully understand a process. So when we're doing an experiment, we gather some data and we want to describe how that data may have arisen or what type of models generate that data. That's when we use the tools of statistics and probability. So Carlos went over this a bit last time, but I want to reiterate basic terminology or basic sort of syntax for how we think about probability. So terms, probabilistic terms, we can think of an outcome. So I roll a dice and I get a number. The number would be an outcome. Or a set of outcomes from a random process is an event. Okay? So if I roll 3 dice and I get a particular set of 3 numbers, that will be an event or an outcome from my sort of probabilistic generative process of rolling the dice. In this case, I have an example. Toss a coin 3 times. We could consider event something like the following: getting exactly 2 heads. So you could imagine tossing a coin 3 times and considering the 3 possible events, or in this case, we're going to consider this one event, getting exactly 2 heads. That will be either a coin toss sequence of heads, tails, heads, 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 tails, or tails, heads, heads. Okay? Either one of those would be an event of getting 2 heads, and we have 3 possible instances of that event. Or rolling dice, the result is even. I could have 3 possible instances of that event, 2, 4, and 6. We consider probability of an event as the total number. I probably have this in the next slide. Yeah, okay. We would consider the probability event. We write the notation like this: the probability of event A. So event A could be something like getting exactly 2 heads. We would denote that probability with this notation, P of A. Or if the probability is rolling an even number, we would denote that P of A. And of course, the formula for that is the number of outcomes that fit event A over the total number of outcomes. So that's the probability P of A for event A occurring. We call all possible outcomes the sample space S, and the number of outcomes in A over the number of total possible outcomes is our probability. This is hopefully basic to you guys. When we think about probability, it's the number of things we want over the total number of possible things. This number is always positive. This number is always between 0 and 1, because I can't have more events than total possible things that can happen. So probability is always between 0 and 1, and it is always positive. And it's denoted P of an event A, or P of a condition A. Some set of things. Okay? Hopefully that's straightforward. Oh, I should have these build one at a time. So, typically, in real-world scenarios, we're not dealing with just counting the total number of possible events and putting them over the total number of possible things that can happen. That's often simple. Too simple for what we need. So instead, we use a model. Okay? And a model, sort of like what we did with the linear regression lecture, has parameters theta. It's typically described as having some shape or having some features. And we usually describe those parameters of that model theta to describe our probabilistic model in this case, instead of just considering some simple fraction of events. And these models are functions of a variable that represent all possible values of events given in the set S. And I'll make this a little bit clear moving forward. And these functions generate probability distribution over all possible event values. Okay? So the most basic probabilistic way of thinking about things, we'll talk about what's the probability of a heads given 5 coin tosses. You can say, well, how many times can I do that over how many total possible things? You calculate a single probability. But in probabilistic modeling, we typically want to describe an entire system. So we say, what's the probability of getting any number of possible events? And we describe all of those processes with a model. And I will give you guys an example of this. Let's say, well, we can actually jump to actually, we'll do this. So the notation for our probabilistic model is we have some set of probabilities describing some events given some parameters. And the parameter, basically, we want to say that our probabilistic model is defined by some parameters that generate some samples x. So I guess all I mean to define here before we get to a concrete example, because this might not make too much sense without a concrete example, is I want to just give you guys some notation. So I'm calling theta the parameters of the model. I'm calling x the samples drawn from that model. X is heads or tails. Theta is the parameter describing the probability of all possible events. Great. So in general, when we deal with statistical models, we define something called random variables, which take on values in the sample space. So this can be something like heads or tails, or something like a roll dice of 1, 2, 3, 4, and 5. We denote that with a capital X. And then we say, drawn from a random variable, capital X, I can draw a particular event, little x. This is just sort of probabilistic notation. And so when we have some model, P of the probability of a given value x, we can alternatively think of that as the probability of a random variable which can generate any number of events, capital X, taking some random event x. I think this will all become more clear when I step through an example. Basically, this all leads to the following form. I want to have the probability of x, which is an event, so it's something like heads or tails, or it's something like 1, 2, 3, 4, 5, 6, described by a parameter theta. So we write that notation as probability of x given theta. This is sort of a basic probabilistic model, right? And I can consider x at many different values. So x, if this is the roll of the dice, x could be 1, 2, 3, 4, 5, or 6. And our notation for that is x is a random variable. So you can actually, sometimes you might just see this notation, you might see this big X notation. That means it can be 1, 2, 3, 4, 5, or 6. And it takes on any particular value, one of those numbers, 1, 2, 3, 4, 5, 6, if I'm rolling dice. And we would write that as capital X, a random variable, equals, takes on some value x. So maybe x equals 1 in this case. But I realized I just want to, this actually isn't super important for the main concept, but when you guys encounter this type of thing, but again, you might see the concept of a random variable in statistics. And it's different than a given event that I've described. A given event that happens, a random event, like rolling a dice and getting a number, is described, frequently the notation is some small x, but in our probabilistic world, we can think of that random event as a random variable that we call capital X. And I might end up using this notation as we move forward, but the big idea here, the only thing that's really important, is that the probability of all events, the most basic way you guys dealt with this before was we counted the number of things that we wanted to assess the probability of, the number of events. We divided by the total number of possible things. We want a more complete description of that when we deal with statistics. We want to figure out what's the probability of all possible outcomes in a model. What's the probability of a neuron spiking 0 times, 1 time, 2 times, 3 times, etc. And I describe that with a distribution. And that distribution's shape is governed by a theta. Okay? So let's say that one more time, and I think we'll go through an example of that. So again, just going back to, well, we'll go through an example of that. So, yeah, so let's do this notation again, citing now real examples, and trying to give you guys the terms for probabilistic thinking, where instead of just counting events and dividing by total number of events, we want to think of complete descriptions of describing entire processes. So how do we do that? We say, well, our probabilistic representation is going to have some shape, and that shape's going to be governed by some theta. And that probabilistic model is going to generate data for us. When I go and I do an experiment in neuroscience, and I gather some spikes, and I want to make sense of those spikes, I have to think of what are the ways I can possibly make sense of these spikes. My goal as a data scientist or as a neuroscientist is to say, let's see if we can describe the process that generated all of this random data. So how might I do that? Well, I say, I don't know exactly what this is going to look like, but I'm going to say it's governed with some shape, and that shape's going to be described by theta, and I'm going to assume the following holds. I'm going to assume that there's some theta that represents a probability distribution that generates data. Some of that data might be unlikely, some of that data might be likely, and what I'm observing is samples from that generative model. Okay? And this is sort of just a big picture here. And we can call, for example, coin flipping, which is what I described before, in this framework, our theta might be something like how weighted is the coin. If the coin always turns out to be heads, we might think that coin is weighted in the favor of always drawing heads. Okay? So maybe the model to describe that process is governed by a parameter like how weighted is my coin. And given a coin, maybe the coin is not weighted at all, it's just a normal coin. It has a 50-50% likelihood. The probability of getting heads or tails is 50%. The random variable x can take on heads or tails. And so thinking about my data, observing a sequence of heads or tails as being drawn from a model that describes probabilities as a function of a parameter, say how weighted my coin is how we think about this problem in the context of statistics. And it's how we use the terminology of statistics to describe coin flipping. Okay? You can also think about this terminology of statistics to describe a variety of things. One example might be spike counts. So I say I observe some neuron for some certain amount of time, and I observe some number of spikes. Maybe I do this 1,000 times, so I observe 1,000 bins of some spike count. Okay? How does a statistician think about this problem? A statistician thinks about this problem as saying, I want to describe all of the possible spike counts I could possibly observe, and I want to describe sort of their shape or the probability that I generate each one. So I assume that this data is governed by some probabilistic model, and that probabilistic model is governed by some theta, and maybe the theta in this case is something like the average number of spikes I get. Okay? And the process of this, and the process of everything sort of we're going to do in these last 2 weeks is figuring out how do I look at my data and figure out my theta. Yeah?
Wait, for that example, does that assume that it's going to be a normal distribution around the spectrum?
That assumes actually something else. It assumes the distribution has a different form. But you were right in pointing out that it makes a distributional assumption. But it's not a normal assumption in this case. It's actually a Poisson assumption. Actually, it could be either one. No, you're right. In this case, I haven't told you everything because I haven't actually written out for you the form of P, a spike count given a theta. This actually will have some form, and it could be normal. Or
I see. So theta, but that's not part of theta. Like the entire set of P of each spike given theta is not described by theta alone.
It's not described by theta alone, exactly. Exactly. Like when I observe some data, I have to make one big assumption. One is like, what class of models am I going to pick? I can't just pick anything. When we did linear regression lecture, I said something like, when I observe some data, I'm going to make some assumption of my data. I'm going to assume it's all linearly related, so everything's described by a line. I'm actually right now trying to make a more general assumption than that. I'm saying it's described by, we don't know yet. It could be lines, it could be normal distributions, it could be a bunch of other different things. We're going to go through different examples of this. But all I'm trying to communicate at this point is the goal of statistics is to say, our data that we observe in the world is described probabilistically. All possible events that can happen in that data are described with some probability. And the shape of that probability distribution is described by theta, and is also chosen beforehand to some extent, like it's normal, or like it's Poisson, or like it's a line, etc. Okay? And so, all I'm trying to communicate to this point is that this process is sort of the terminology for how we think about these things. And if we think about generating data from a probability distribution, we usually call that probability. And if we talk about taking data and inferring a probability distribution, we often call that statistics. So if you're in a probability class, your goal is to figure out different shapes of these guys. How do I characterize theta, and how can I characterize theta to describe probabilities of events in the real world? If I'm in a statistics class, my goal is to look at data and figure out my model. So I look at heads and tails, this random variable, capital X, that takes on heads or tails. I look at some set of instances of this data, a series of heads, a series of tails, and I try to infer what the hell is my probabilistic model. And that's what we're going to do in this final week. So we're going to think about, if you're an experimentalist and you go in and you record spikes, how can you describe what the hell's going on? Right? How can you do that? Well, you look at the data and you assert some probabilistic form, and you try to figure out, well, what are my thetas given that data that I see? And again, I'm saying this really, really generally. I sort of haven't even given you guys a concrete example, and we're just going to go through a couple of concrete examples as this lecture goes through. But it's just kind of a general problem. In fact, this will be the exact example that you guys will probably, well, something like this maybe. last Thursday we had some data generated by some model. That model was the mutual inhibition model. And Carlos talked about how you can think about easy decisions in that model, or hard decisions in that model, as how quickly those data points converged to one side of the, basically one choice or the other choice, one activation neuron or the other activated neuron. Do you guys remember that? So those were, he said one way to describe that was to think about how quickly those trajectories happen. And you can think about trying to describe a model, basically trying to describe the shape of the distribution of how quickly all of those events happen. So I can look at those event times. It was half a second, a full second, 2 seconds, etc. I get a bunch of those data draws and try to infer the shape of those reaction times by determining a theta. And the whole reason we want to do that is then we can make predictions, right? If I have some description of my model, if I have some probability associated with all events that happen in the real world, I can now describe what's happening in the real world moving forward. I talked about this before as the concept of training and testing. I can look at my data, I can train it to find some parameters theta, and if I have those parameters theta, I can use my model to now predict what's going to happen in the future. Right? I can also use my model to try to understand the system, to try to figure out how the brain works, to try to figure out how it responds to stimuli, etc. So this is exactly what I said before. You can imagine the theta being the probability of coin toss, say it's 0.3, maybe favoring in the direction of landing and tails. I draw some samples from my random variable, some events from my random variable x, which can take on heads or tails. I look at those data. Sorry, this direction here is probability, right? This is what I'm describing. If I have some model and I'm generating data from that model, we'll call that probability, but if instead I want to take that model and figure out what my distribution is, I will call something like that statistics. Yeah?
Is it probability or statistics when you get experimental data and see what probability that has conformed to your model?
It's probably still would be considered inference or considered statistics. The process of looking at real data, the process of sort of being a scientist, doing an experiment, getting in data, and trying to figure out a probabilistic form of that data, which is what most neuroscientists do, would be categorized as statistics or statistical inference. I mean, I'll probably use the word inference a lot. By inference, I mean we take the data and we infer the parameters data. If you're a mathematician, you're not interested in that step. Actually, you're often not even interested in particular events from your sample space. You're not interested in values that those random variables can take on and what those values look like. Instead, you're just interested in something like, what are all the kinds of probability distributions I could get? And how might they be related to each other? And how might theta, if one of my thetas gets really, really big, maybe it looks like a different probability distribution. Or maybe they can all be summed up as approximations. I mean, if you're doing that, which is basically just pure math, that's kind of like the mathematics of probability. And just for practical points of view, for your guys' purposes, people who are like probabilistic, let's say they do what would maybe more classically considered probability, would publish in something like mathematical journals. And if you're doing statistics, if you're doing inference or statistical inference, you're generally publishing in something that would be more considered applied or more considered, often we'll deal with actual experiments and actual data. There's clearly blurring between that, but that's sort of a general sense. Let's see what's next. Okay, so I realize I've been sort of vague about what I mean when I'm talking about this probability that's governed by theta. I didn't give you guys an example. And that's because in this class we actually hadn't, except for a little bit last Thursday, we haven't really defined what a probability distribution is. I didn't even really have to do that for the linear regression lecture. And it's sort of key to key to what statistics is. So if you guys could even just for today, leave this lecture understanding what a probability distribution is, that will give you a big missing piece of sort of your mathematical neuroscience bank of knowledge, right? Because we haven't actually really dealt with that in this course much at all. So a probability distribution is, I said this before, but now it's sort of written out, is the probability is associated with every possible event that can be drawn from a random variable. Okay, so again, using an example of dice, a probability distribution is the probability of all possible events of that dice roll, say 1, 2, 3, 4, 5, 6. In the case of dice, the probability distribution is flat, right? A typical dice. Probability distribution is flat. I have an equal probability of rolling every possible event. So if I was considering dice here, I would think of P of x, where x can take on 1, 2, 3, 4, 5, 6, as all having equal values. That's the probability distribution associated with the dice roll where we know everything there is to know about the model, right? We know that the likelihood is equal for all possible things, so I actually don't need to do anything like infer some parameters in this model that I already know. If instead I was considering the probability distribution of dice, I would have P of x. X is my random variable, frequently denoted with a capital X. It can take on heads or tails. And if my probability distribution looks like this, I would say, well, that's some theta, maybe describing the weighting of the coin, where maybe my theta is 0.9. And if instead my probability distribution looks like this, like a typical coin, we would consider this theta to be 0.5. Does that make sense? And a few features of this model, I think Carlos went over this last Thursday, but features of this model, the probability of all possible events has to add to 1. Does that make sense? So if I consider every possible thing that could happen, all of those probabilities added up are the probability that at least something happens, and we sort of assume that something happens. Right? If I roll a dice, I know that at least one thing happens. So the probability of all of my possible events added up should be equal to 1. And any given value here is bounded between 0 and 1. So these are features of probability distributions. The sum over all possible events adds to 1, and any given value of probability, as we know from the first slide, has to exist between 0 and 1. So I've written this out in mathematical notation, but the concept's exactly the same. We can say the probability of some random variable x equaling some event is some f of that event. The f of that event is whatever. In here, you could just consider that p of x2. I think that's okay. And it takes on different values. And most of the time, we're not interested in these sort of flat, simple distributions. We're interested in complicated distributions or distributions over continuous variables. So again, in the case of rolling a dice, I only had 2 events to worry about. In the case of gathering data, it's never really that simple, right? When I record from neurons in your brain, I might get 1 spike, I might get 100 spikes. I might get 1,000 spikes. So I've got a lot of events to consider. Maybe the likelihood of getting 1,000 spikes is very, 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 very small. My likelihood of getting 5 spikes is very high. Right? So that probability distribution isn't something that's just flat. It's something that's high in some areas and low in other areas. And figuring out sort of that exact shape is the process of finding theta in that distribution. Okay. Is that clear thus far? Because that's kind of, like the first main concept, and that's kind of the main concept. Basically the biggest remaining main concept. Is everybody okay? Are we sure there's no questions? Okay. So just some technical points. The cases I've given to you, x can take on discrete values. I said something like heads and tails, or I said something like 1, 2, 3, 4, 5, and 6. Or in the case of spikes, I said something like, well, it could be 0, it could be 1, it could be 100. We call all of those probability distributions discrete probability distributions. They take on discrete values. And they sum to 1. All possible events sum to 1. That's actually a little bit less common, unless we're counting spikes from neurons, which is probably the most common instances you guys will run into. But in the field of all possible kinds of data I can get, I often don't have to deal with things that are discrete. If I'm figuring out the probability distribution of heights in a population, those don't take on discrete values, right? They could take on any number. Okay? So instead of using discrete probability distributions, I would use continuous probability distributions. These are now smooth functions. Instead of them adding to 1, they integrate to 1. The same properties hold. They're bounded between 0 and 1 for any given random event. Any given random event is some, in this case, real number. That's what this, maybe you guys haven't seen this notation before. X looks like a weird looking E, capital R. For those that haven't had mathematics classes, that means X can take on any real number. Instead of X taking on 1, 2, 3, 4, 5, 6, it can take on some continuous distribution of numbers. And so the model to describe these kinds of data are going to be continuous probabilistic models. But it's the same process. I draw some data, I try to figure out thetas to describe the shape of my probability distribution. This is probably also worth pointing out. The probability of getting any exact event in a continuous probability distribution is actually infinitely small, because it's an infinitely thin slice of that X. So in order to assess finite probabilities for a continuous distribution, I have to make this kind of assumption. What's the probability that X lies between some interval between, say, A and B? In that case, X is not infinitely tiny sliver, it has some width, and therefore the probability has some finite value. So some technical point. And actually, people get tripped up on this all the time in real life. I've gotten tripped up on this before in my own research, forgetting the fact that for any given specific event, the probability of that specific event is going to be 0 because that probability distribution is infinitely narrow. That slice of P of X given X, you can think of that F of X as also P of X given X is very, very small. But the probability X lies between, say, 5'10" and 6 feet in a population, it's going to have some finite value. Again, you can think of it like population. What is the probability that I take the height of a given individual and they are exactly 5'10.000000000 inches, right? It's basically 0. I'm never going to actually find that. But instead I say, well, what's the probability that's between 5'10" and 5'11"? That's got some width to it. That actually has a finite probability associated with it. The mathematical notation for what I just said would be we integrate the continuous distribution between two small values that has some finite probability. And of course, the integral over the whole probability distribution from negative infinity to infinity is going to be 1. Okay? Great. So now we are familiar with distributions and continuous and discrete distributions. Okay. Now I'm going to give you guys just names of different kinds of distributions. These different kinds of distributions are always asserted beforehand. I make this choice when I'm doing my experiment. I look at some data and I say, maybe this is described by a Bernoulli distribution. Maybe it's described by a binomial distribution. Maybe it's described by Poisson. I make that assertion beforehand, and then I can look at my data and figure out the exact theta that governs the shape of that distribution. So here, these are all discrete probability distributions. In fact, a binomial is the coin toss example that I gave you before. It's the way of describing this function here according to some theta. Only I probably didn't call it theta, I called it p. So just so we're clear as to notation here, in this Bernoulli, I would say theta is p. There's only one parameter describing the shape of that distribution. There's only one parameter describing the shape as I move along the values of x. In that case, x is only 0 and 1, or heads and tails. In binomial, theta is going to be two things. It's going to be the set n and p. And in Poisson, theta is going to be just one parameter, and it's called lambda. These are just conventions. We call, for the Poisson distribution, we call the parameter describing its shape lambda. For the Bernoulli, we typically call it p because it's just the probability of an event. For binomial, we call it n. You don't actually have to know any of these in detail, though you are very likely, if you continue in neuroscience, to encounter Poisson a lot, because that's the shape we use to describe spikes. But the other two, you may encounter it if you go into, data science in some form, you are very likely to encounter it. But for this class, we don't really need to worry about either of these. In fact, I don't know how much any of the specific forms might come up. By far the most common one is a continuous probability distribution. You are incredibly likely to encounter this in your life, even if you literally never see statistics again, just because it comes up everywhere. It'll come up sort of, if you're ever just even like reading about what's going on in the stats world. That will be the Gaussian distribution, right? But I think we've talked about that a little bit before. If the data I observe takes on real numbered values like heights, and I don't know anything else about it, I usually describe it with the Gaussian distribution. It's like by far, probably 10 to 1, the most common used continuous, the most common used probability distribution in general. And there's lots of reasons for that, but the most simple of which is if I don't know anything else about the system and I know it takes on real numbers, I'm probably going to use a Gaussian probability distribution to describe it. In the parameters of those distributions, the theta is going to be my u. Oh, sorry, that should be a mu up in the top right. So mu and sigma, mean and variance. Right, when you guys take statistics in high school and you get some data and you calculate what's the mean and what's the variance of that data, what you're actually doing is figuring out the parameters of a Gaussian distribution to describe that data. That's why you did it. And because we use Gaussian so much, it was like the simplest thing to do. When you have any data, you figure out its mean, you figure out its variance, turns out you have its whole shape, that whole bell curve shape now, and describe your data. There's also something called a multivariate Gaussian. That's if instead of drawing one number, I draw 10 each time. So what do I mean? I mean, instead of this being a scalar, it's a vector. So I'm trying to model heights and weights of an entire population. We did this before. When we talked about linear regression, when we talked about PCA, we talked about our observations being more than a scalar. We talked about our observations being a vector. And the generalization of the Gaussian distribution is just called the multivariate Gaussian distribution. There's a lot. There's whole courses on these things. I'm showing you the form here. Don't worry too much about all of that math, because we don't have time to go into it, because we have one class left. But those are all basically matrices. And you would now, actually, like moving forward, if you go on to another data science class, almost certainly, you take another data science class that will build on the stuff you learned from this one, the next thing to do would be to tackle this multivariate Gaussian distribution. Figure out, how do I describe my data in the real world, but instead of using scalars, use vectors? And how do I do sort of inference on that, and how do I figure out how to model that kind of system? You're guaranteed to use that distribution. But again, outside of the course, I just want to give you guys a little bit of perspective as to kind of what you would do moving forward and where this sort of sits in the space of all the possible things that people kind of do. Exponential, whatever, we don't have to worry about it. I don't really need it. I just put it there so we'd have 3 on each. I almost never use it either. I mean, whatever. Does that make sense? So these are just examples of distributions. You assert them beforehand. You draw your data. You figure out your theta. Your data has some form, some event. Heads, tails, 1, 2, 3, 4, 5, 6, or any number, etc. That event is drawn from our instances, our events of a random variable that I call capital. I called capital X in the beginning. Any questions up until this point? Even big questions about like what are, if you don't have a sense of why this is important, or if you're confused about the generality of this or why we would do it, you could also, I don't know, ask about that. So I think, well, we'll get there. Okay, so now what I want to do is build up the pieces to describe Bayes' rule to you using the terms I just defined and using the notation I just defined. Because if I do that, then we have a complete picture of sort of Bayes' rule sort of built up from this idea of distributions. Because I think when Carlos said it last week, we didn't necessarily have the foundation, we weren't thinking about it in this way. So what Bayes' rule crucially depends on is two different events happening. Okay? So it's not the probability of just one thing happening in general. Bayes' rule depends on the probability of one thing happening and the second thing happening. The example Carlos used was, let's say something can be, I do some scenario that can be either A or B, and then I have another draw that's either 1, 2, or 3. You guys remember this example from last Thursday? So he said two events happened. I either drew an A or a B, or I got an event I got an A or a B, and I got an event 1, 2, or 3. I had 6 possible outcomes. Okay? But I can consider that probability distribution over two random variables. The first one taking on the value of either A or B, and the second one taking on the value of either 1, 2, or 3. Okay? I've drawn that actually. Yeah, sorry, I wanted to do it like this. Let's pretend, ignore the shaded figure I had up before. Let's pretend I'm doing the same thing. Only this time it's A, B, C, and D, and 1, 2, 3, and 4. Okay, so this is just basically recapping last week. I just have 16 examples instead of 6 examples. Okay? The probability of, so in this case, two random variables. I'm just calling them y and x. I could call them capital Y and x. Don't use a random variable notation. Call them y and x. Y can take on A, B, C, D. X can take on 1, 2, 3, 4. Okay? So any given coordinate here is a draw of, is a probability of getting, say, x equals 2, y equals b. That's that 0.14 in the bottom right, let's say. Okay? Because these are probability distributions, and I've got two possible events, all of my probabilities will add to 1, because I'm sort of assuming at least one thing happened, or one thing happened. So all of those probabilities added up should be equal to 1. If I did my math right, it should be equal to 1. And the probability of any given pair of events would be the lookup value in one of those slots. That makes sense, right? Everybody's okay with all this? So, a couple of the things we can do now that we have a distribution of this form is think about what happens if I only want to consider my probability over one of these events. So if I only want to consider my probability over x, which takes on 1, 2, 3, or 4, what I can do is sum along the probabilities of all of my A, B, C, or D. Right? This should be a recap, so hopefully this is intuitive to you guys. This isn't intuitive, tell me to slow down. But I can take this probability function that is now over two variables, x and y. So just so we're clear, it's not going to be the sum, it's going to be the sum over all x values and all y values that adds to 1. If this was continuous, it would be an integral over x and y. It would be a double integral. That would equal 1. But if I have a distribution over x and y, and I want to only consider my distribution over just one of the variables, I do an operation that in statistics we call marginalization. You might hear this moving forward. This is because we take It's called marginalization because we take this probability distribution that's over 2 dimensions and I squish it down and make it over 1 dimension. They think of that squishing process as putting in the margins, literally. And so this is called marginalization, like figuring out what's on sort of the sidelines of these distributions. This process of marginalization works by summing along this direction and getting some distribution over only x. I could actually marginalize the other way. I could sum over all my x's and get a probability distribution over y. If I add all these up, now I have a discrete probability distribution, like the form I just described. It's some function of x, p of x given x. If I want to describe it with a model and figure out those models and parameters, I can do that, given some observed data. Make sense? Okay, new terminology. There's another thing we can consider in this framework, and that's considering the probability of y conditioned on a particular value of x. Okay? So what I do is I say something like, well, let's say x equals 1, or sorry, 2, whatever that is. Now what's my probability of y? That's like finding this row. But I got a problem. This row doesn't add to 1. So in order to marginalize, I have to divide this entire row by the total value of the whole thing in that row, of all those probabilities added up. This is, I also think, what Carlos thinks. Does that make sense to everybody? That's called a conditionalization. That's like finding something like p of y, the new notation here, and if anybody's unclear with this notation, stop me. It's this notation. You guys will likely see this. P of y given, that vertical line is always described as given. This is the probability of y given the fact that x took a value of, sorry, I said, oh yeah, okay. I correctly labeled my x's too. Probability of x given, say, -1 here. Sorry, probability of y given x equals -1. Okay, in order to figure that out, I have to take the joint probability where y, the joint probability of y and x equals -1 and divide it by the probability of x equaling -1. Okay? Sorry, let me say that one more time. I don't think it was clear. The probability of x equaling -1 is all these guys added up, right? I can take that and divide out just what's described by this row, and then I get a total, good to go, viable probability distribution, and that's p of y, x equals -1. So I don't want to get too tripped up on the notation. The thing I have here on the left is a totally viable probability distribution. The thing I have here on the right is just the probability of y, comma, x equals -1. So the probability of y and x giving me -1, not the probability of y given x equals -1. I hope that's not too confusing. Does anybody want me to step through that one more time? You guys got it.
Could you maybe just say the values that would correspond to this case?
Great. Yes. So the value of p of y given x equals -1 is all of those values divided by all of them added up. Sorry. So that's going to be the value on the left is 0.03 is a function over y, and it's going to be 0.03, 0.07, 0.14, 0.07, all divided by that added up.
Right.
Okay?
Yeah.
And just those numbers is that top right, without the division.
Just the individual.
Correct. It would still be, I mean, they're both functions over y. So both the left and the top right are functions over y. One of them is properly normalized, and I use this word. Sorry. So the process of normalization is taking the thing and dividing it by its total sum, and that makes it add to 1. Process of normalization. So the left-hand side of this is properly normalized. Great. So now let's think about this in the continuous case. We shouldn't have any trouble here. All the intuition follows exactly analogously. Instead of summing, I integrate, so this is a double integral. Probability distributions over 2 possible values, x and y. If I integrate all of them, it adds to 1. If I marginalize, I basically sum, so I integrate out, or I add up. Continuously add would be like integrating across y here. Integrate through y to get a probability distribution over x. This is sort of the grown-up version of what marginalization looks like. Marginalization, in most cases in statistics, is I take an integral over the variable I no longer want to consider, so I sum over all the y's, I integrate over all the y's, and I get a distribution only over x. That's in the marginals, and that's my marginalization. This here is a multivariate normal Gaussian distribution as an example, just because this is very easy to generate and easy to make these calculations. One of the reasons why we use Gaussian distributions very often, because these kinds of calculations are really nice. But you guys do not have to know them for this course. Great, you can imagine doing it the other direction, integrating over x, getting a probability distribution over y. Is that clear? Okay. Conditionalization is the same thing. You can think about taking a slice of the network. All of the same intuitions hold. One thing I want to show you, if I take a slice of this and then divide it by its whole thing added up, and I do the same thing here, and I do the same thing here, and I do the same thing for all of the slices, I can actually draw a new two-dimensional distribution. Sorry, let's do that. Oh, and it looks like this. So you can see here, this shape is a probability distribution of the two variables, x and y. If I want to figure out the conditional x given y, I can think about the conditional of, I want to think about the conditional y given x. I can think about, well, what's the value of this conditional when x equals -1? What is it when x equals -0.9? What is it when x equals -0.8? I can do this for all of them, all possible values of x. I can divide out the total value among all of these guys. And I get a shape that looks a little different now. It'll look like that. So now I have p of y given x over that whole distribution, where actually all of these guys added up is greater than 1, but along each row it's exactly equal to 1. That's what I'm trying to say there. So x could take on any value. If it took on the value of 0, I would have a totally viable probability distribution along y for 0. But if I said, oh, well, what's the probability when x equals 2? I would have a different distribution with a different shape of y. Does that make sense? A little bit? Some people not convinced, but other people are confused. All I'm saying here, this is a different way of writing this conditional distribution, p of y given x. If I have p of y given x, no matter what value x holds, y should be a viable probability distribution. So y should all add to 1. So along each row, along each column, the distribution will add to 1. That's sort of all I'm saying. These are called conditional densities. You can do it the other way. I don't think that's super important. Is that straightforward? Okay, so here, maybe I wanted to say, so yeah, like I said before, this conditional distribution is like taking the joint distribution, the distribution over two variables, and dividing out the probability for x equaling every one of those values. So I'm dividing out the probability of x. Right, I showed this as an example for one particular example before. I said something like, what's the probability of y given x equals -1? And then we said that was the probability of y comma x equals -1 divided by the probability of x equals -1. In this case, I'm doing this for all possible values of x, so I've just dropped the equals -1. X could take on any value. This relationship still holds. Okay? To get to Bayes' rule, we use this relationship. I could write it like this, or I could write it like this. That's the other way. Just thinking about this in the other direction, dividing by the different probability. if I have this relationship and I have this relationship, I could write them both out like this. And you can actually see here that P of x comma y is present, can describe a relationship of both y given x and x given y. And I can use these two equations to generate Bayes' rule. So typically this is written like this. P of x given y is equal to P of y given x times P of x divided by P of y. And I defined all of these terms already, but you are, again, almost certain to see them in some form forward. The terms of these pieces of Bayes' rule. This is used, this sort of rule is not just, let's just say, it's more powerful than it seems right now. This relationship of taking a probability distribution over two variables, two random variables, x and y, and describing them in terms of their conditional distributions actually represents an incredibly powerful framework to think about all kinds of statistical models. And so when I write out Bayes' rule in this form, everything has a name. This is used so often that every term in this little equation is given its own name. The P of y given x, this is typically terminology. The thing that goes here is often called the likelihood. We divide the likelihood by a prior, that's something governing the x, and we divide it by something called the marginal probability, or the marginal, since you just did marginal, and it's equal to something called the posterior. Everything in this rule has a specific and special name. Now thinking about this back to the modeling I was talking about before, very often in statistics, we draw some data. We call that data y, and then instead of calling this x, we might call it theta, the parameters of my model. So frequently, you'll see this, well, I don't need to write it out. It's the same thing as replacing x with theta here, and it's the process, it represents the process of inferring parameters of a model theta given some observations x, given some data observations x. So x could be something like ones and zeros or heights in population. Theta can be something like the model parameters, and I can use this rule to describe the probability of my model parameters given some data. That's the goal of Bayesian statistics. What's the probability that the mean height of my population was actually, 5'8". The process of finding the probability of that theta, that mean value being equal to some exact value, is actually calculated in this case. So that's why we do Bayesian statistics. It's a way of inferring models. It's a way of taking some data in the world, y, inferring some parameters, theta, or in this case, x, and trying to describe all of these pieces to figure out what does my model look like? What does it probably look like? That's this. So again, thinking about what you guys have to do more practically, if you were given some, say, reaction times in a model, say you get some data of how fast a decision's being made because two populations inhibit each other, for example, I have a certain set of reaction times. That's my data. And I want to figure out my theta. And maybe I want to figure out my theta knowing that the theta shouldn't be something crazy. So maybe I put what's called a prior on theta. And then I have some way of evaluating the likelihood that the likelihood that that model parameter is actually the value I guess it is at. And we'll talk about different ways of doing that I think I already went through this. Okay, so we'll go through a concrete, very, very simple example of how you might use Bayes' rule in a very, very simple context. Imagine the following scenario. You have a fake coin. It has heads on both sides, and you have a real coin. It has heads and tails. And you don't know which coin you are given. All you have is draws or samples from that coin. And your goal is to figure out, is it fake or is it not fake? You can actually use Bayes' rule in this context to do this problem. So you grab one of these coins at random, you flip it, it comes up heads. What's the probability that you're holding a fake? You can use Bayes' rule to solve this kind of problem. You can actually just work through all of the probabilities. What's the probability of it being fake, given that you got a heads? Or what's the probability of it being normal, given that you got a heads? That's what we're calculating, right? Well, we know that that's equal to or proportional to the probability of it being heads, given that it was a fake, times the probability of it being a fake. Okay? So what's the probability of it being heads, given that it was a fake? It's 1. And the probability it was a fake is 1/2, because I grabbed the coins at random. So what's that equal to? It's equal to something like 1/2. Let's do the other one. What's the probability of it heads? Given it was normal, well, that should be 1/2, and the probability it was normal is also 1/2. So the likelihood of this event happening is equal to 1/4. The likelihood of that event happening is equal to 1/2. But of course, these guys have to add to a probability of 1. Because one of those two things definitely happened, so I have to normalize here. I have to sort of divide by p of y. That's kind of this step. And so if you grab a coin at random, flip it, and it comes up heads, the likelihood of it being fake is 2/3. Does that make sense? So let's say the opposite happens. Well, okay, that makes sense, right? 2 out of 3, it was fake. You have a start, you got either fake or normal. You draw heads, 2 out of 3 of those instances, you will have fake. Yeah.
How you got the denominator? Because 1/2 plus 1/4.
Oh, great. Yeah, so all I'm doing is normalizing. I'm taking the total probability of things that could have happened and adding them up. So I either had this, which was 1/2, or I had this, which was 1/4. So add it together. It's 1/2 plus 1/4. That's sort of the total. This is because, this whole thing alone is a product of two probability distributions. It's not a probability distribution itself. And what I'm doing is figuring out the likelihood according to each of these scenarios, because I know it has to be one of those two scenarios. I can normalize them, make them add to 1. And then in this case, these two will now add to 1 because it was at least one of those. Okay, you could do the same thing if it comes up tails. This is a much more trivial example, right? Because if it comes up tails, your probability of it being a fake is 0. Because the fake had 2 heads. Your probability of it being normal was again 1/4, but I normalize. The sum of 0 and 1/4 is just 1/4, so I divide each of these by 1/4, and I get 1. So the certainty, of course, if it came up tails, that I was holding in normal. That make sense? It's a very simple example of implementing Bayes' rule with a prior. The prior being the probability of it being fake or not fake. Okay, cool. This is just a fun example. We only have 10 minutes left, so we'll leave with a fun example of how people think about Bayesian statistics. So one of the ways Bayesian statistics one of the more common implementation of Bayesian statistics in neuroscience is thinking about this rule in the context of sensory information or information coming in to your system from the outside world. And the reason that's important is what the brain is basically trying to do is wants to figure out what's in the world given some sort of input information that you have. Given some sort of visual image, I want to figure out what's the actual thing in the world that gave rise to that visual imagery in my head. Okay? So that can actually be written as the probability of what's in the world given what comes into my head is proportional to the probability of what's in the world times the probability of what's in the world and the kind of data it generates. Okay? So if I'm... Wait, does this just dive straight into the example? Yeah, okay. So this is famously, well, not really famously, but Helmholtz has a quote describing this. Perception is our best guess as to what's in the world given our current sensory evidence and our prior experience with it. So if we're used to seeing something really, 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 really often, if the sensory information lends itself towards looking like that thing, I'm going to probably infer that that's the thing in the real world. Because I'm going to be manipulated by this prior information, by this probability of what's in the world. And we use this construct of probability sort of pieces to make inference in neuroscience about, given some sensory data, what's in the world, right? And so here's a kind of compelling, so okay, perception is our best guess as to what's in the world given current sensory information and prior experience. And this can lend itself to, actually this is basically how most optical illusions are described, and this is a particularly cool one. So actually, I don't know if this is going to make noise. Can we hear this? Okay.
This is the hollow head. Actually, at the moment, it's a perfectly normal head of Charlie Chaplin, but wait, as it comes round, you'll see, or will you, that it's hollow. The back of it, coming round now, is actually a hollow mask. It appears to rotate in the opposite direction, and amazingly, the nose sticks out, although it's actually sticking in. Coming round now is the normal, correct as it were, face, and wait again as it comes round, and you'll see this extraordinary thing like Jekyll and Hyde. Both the noses stick out because it's so unlikely that a nose sticks in that a face is hollow. So you see it as convex, although it's in fact concave, as now, and then it'll become the normal face again, there. And note that as soon as the features are...
Okay, that's cool. You guys get the idea. So anyway, this is a popular example of how our prior on the world, or the likelihood of something happening in the real world, shapes, that the prior on that information sort of shapes our interpretation of sensory data. It's a very famous example of how Bayes' rule is used in sensory neuroscience. It's sort of just that same thing again put in context. Of course, we have two hypotheses given that sensory information. One is that the face is convex, and one is that it's concave. And of course, we can consider two posteriors. The probability it's convex given the video is proportional to the probability of the video given it's convex times the probability that it's convex. Right, now in our real world experience, we almost always see convex things. We never go around seeing concave faces. So our prior, the probability of a face being convex is really, really high here. So it's going to bias our interpretation, always interpreting that face as convex. Do I have something like that? Yeah. So because the probability of convex is so much bigger than the probability of concave, the posterior probability, this final term, of convex is always higher. And this determines how we interpret that sensory information. And just to sort of recap, Bayes' rule is used more generally than this, but this is a fun example in sensory neuroscience of how people have tried to make sense of how we interpret ambiguous data around us. How when information comes into our brains, we use the likelihood that that information gave rise is coming from a particular thing in the real world, like the likelihood that it's actually coming from a convex shape. or convex space in this case, to shape our interpretation. But Bayes' rule is actually even more general than that because it's a big framework to generate a probabilistic description or a posterior description of the interpretation that we have given the information that we observe in an experiment. So it's actually really general. This is a fun toy example, but if you think of video as what I get from an experiment, and you think of concave as how a scientist interprets what it gets, this framework can be used in a huge sort of variety of contexts, because it's a way of describing how confident I am about my interpretation given some observed data. And we can end there. There's another example. Because we like seeing cubes as pointed out, you can see these kinds of fun illusions of cubes looking like they're pointed out even though they're actually pointed in because our prior shapes that model interpretation so strongly. It's sort of, you can think of theta here as the way we interpret this sensory data. Cool? Okay, any final questions about any of this stuff? So I didn't get to estimation, and we'll probably do that Thursday, but thinking about these pieces, thinking about priors, likelihood, and model parameters, and we can use data to infer model parameters and shape them in particular relationships, is probably what you're going to need for sort of the final piece of this course. Great, thank you.